Every device on the internet has one basic need: an address. Just like you can't deliver a letter without a house address, data can't move on a network without an IP address. An IP address is a unique identifier given to a device on a network. They don't describe your computer, they describe where your computer lives on the network.
Let's start with the two types of IP addresses. IPv4 is the one you see most often. It looks like this: 192.168.1.1, 4 numbers, each between 0 and 255. IPv4 has about 4.3 billion addresses. IPv4 worked great until the internet exploded. We started running out of addresses, so we introduced IPv6. It looks like this.
Yes, it looks scary, but it solves one big problem. IPv6 gives us an almost unlimited number of addresses. Now here's a special one: 127.0.0.1. This is called the loopback address. It means this computer is talking to itself. Tools like Burp Suite often run on 127.0.0.1 because they're meant to intercept traffic locally, not from the internet. The next question is, how does data actually move between those addresses? The TCP IP model is the model the internet really uses. The TCP IP model has 4 layers. At the top is the application layer. This is where user-facing protocols work. When you open a website, you're interacting with this layer. Protocols like HTTP, HTTPS, FTP, SMTP, and DNS live here. Below that is the transport layer. This layer controls communication between applications. It uses port numbers and protocols like TCP and UDP to decide how data should be delivered, reliably or fast. Next is the internet layer. This layer is responsible for IP addressing and routing. It decides where data should go and how to reach the destination across different networks. At the bottom is the network access layer. This layer handles local delivery. It works with MAC addresses, frames, Ethernet, and Wi-Fi to physically send data out of your device. Transmission Control Protocol operates at the transport layer of the TCP IP model. This means TCP is responsible for process-to-process communication, reliability, and ordering of data. To do this job, TCP attaches its own header in front of the actual data. This TCP header sits in front of your data and tells TCP how to manage the connection, how to order the data, and how to make sure nothing is lost. Let's start with the most important fields: ports. At the very top, you see the source port and destination port. These ports identify which application is talking on each side. For example, your browser might use a random source port, while the destination port could be 80 or 443 on a web server. This is how TCP knows exactly which application should receive the data, not just which device.
Next comes the sequence number. TCP breaks data into smaller chunks, and the sequence number tells TCP the exact position of this chunk in the overall data stream. Even if packets arrive out of order, TCP can put everything back together correctly because of this number. Right below that is the acknowledgement number. This field tells the sender, "I have successfully received all data up to this point." This is how TCP confirms delivery and detects missing data. Together, the sequence number and acknowledgement number are the core reason TCP provides reliable and ordered communication.
All right, let's zoom in on the flags in the TCP header. The first flag we care about is SYN, short for synchronize. This is like knocking on the door. When your computer wants to connect to a server, it sends a packet with the SYN flag set, saying, "Hey, I want to start a conversation. Here's my initial sequence number." Next, the server replies with SYN plus ACK. That's 2 flags at once. SYN, the server says, "Got your knock. I want to talk too. Here's my sequence number." ACK,
It also acknowledges your initial sequence number, and I received your knock loud and clear. Finally, your computer sends back ACK alone. This is like saying, "Great, I got your confirmation. Let's start talking."
And that's the three-way handshake. SYN, SYN-ACK, ACK. Just 3 packets, 3 steps, and a connection is established. Other flags are used later. FIN is like saying goodbye. The connection wants to close. RST is the abort mission flag. Something went wrong. Drop the connection immediately. So, in short, SYN opens the door, ACK confirms, FIN closes it, and RST bails out. Understanding these flags is critical in cybersecurity because tools, scans, and attacks often manipulate these exact bits.